guys, how are you today? So today I will be finally explaining AP Chemistry Chapter 4. As always, of course, I'm going to divide them into sections, and we start with the very first section, which is talking about shapes of molecules. So shapes of molecules and the VSEPR theory. VSEPR stands for valence shell electron pair repulsion. So they start off the chapter or the section by talking about the shape of a molecule. The shape of a molecule is the three-dimensional distribution of the molecules, atoms, and space. So we start the shape of a molecule. Not without the S, is the three-dimensional 3D distribution of the molecules, atoms in space. It plays an essential role in determining the properties of the molecule. So once we know the shape of a molecule, we will be able to find out what we will be able to determine the properties of the molecule. So we say that it determines the properties of the molecule. Now I'm gonna open a new page, and in section 4.1 they start by discussing how do we determine the shape of the molecule. To determine the shape of the molecule, we use different type of waves, and these waves are of course electromagnetic waves. So to determine shape of molecule, we have first of all microwave radiation. What does microwave radiation do exactly? It's molecules in microwave radiation. Basically, microwave radiation will probe the rotational energy levels to determine the shape of the molecule. Okay? So in order to determine the shape of the molecule, we will use what? We will use microwave radiation. Now, to study the chemical bonding in molecules, so I will make a new line, to study chemical bonding in molecules, we use infrared radiation. Use infrared radiation. Okay? Now, to study the transmission of electrons, or sorry, the emission of electrons from one energy level to another, we use ultraviolet and visible light. So I will call this 1. This is 2. Now 3, to study emission of molecules from one energy level, which is N, to another. What do we use? We use ultraviolet, UV radiation, and visible light, VL, okay? So 3 important waves to know. Microwave radiation, it's used to determine the shape of the molecule. To study chemical bonding in molecules, we use infrared radiation. And to study the emission of molecules from one energy level to another, we use ultraviolet and visible light. Now, as we continue throughout the chapter, they start talking about the shape of the molecule and how do we discuss and determine the shape of a molecule. The shape of a molecule, first of all, depends on the number of electron pairs surrounding its atoms, okay? So the shape of a molecule depends on the number of electron pairs. E minus means electron pairs surrounding its atoms. Now, what do we mean when we talk about electron pairs? This we're talking about both bonded electrons, so bonded electrons, and lone pairs. So both of these, we're talking about them when we say the electron pairs surrounding its atoms. That means we consider both lone pairs, which is the 2 dots, and the bonded electrons, which is the bond. Now, what about the electron pairs? Electron pairs orient themselves, like naturally they orient themselves as far as possible to minimize the repulsion between them. Okay, so they orient themselves as far as possible to minimize the repulsion between them. To minimize the repulsion between them. Now, this is very essential because we know that electrons, of course, they're going to repel each other, right? So, in order to minimize this repulsion, okay, they orient themselves as far as possible. So, this is from where we got all of the different possible shapes, because this is, in all of these shapes, this is the maximum that all electrons, especially the bonded pairs, can stay apart from each other. Because of this, theory, this is what started the VSEPR, okay? And what does the VSEPR states? VSEPR states that the Coulombic repulsion between the pairs of electrons, the Coulombic repulsions between the pairs of electrons surrounding the central atom, determines the shape of a molecule by orienting the electron pairs as far apart as possible to minimize energy. Very important. Okay, so basically what we said here literally states the VSEPR theory. Okay, so determines the shape of a molecule by orienting the electron pairs as far apart as possible to minimize energy. So basically, if they asked you in the exam to state the VSEPR theory, you would say that the Coulombic repulsions between the pairs of electrons surrounding the central atom determines the shape of a molecule by orienting the electron pairs as far apart as possible to minimize energy. Now, actually, let's take a very nice and easy example of that. We would take the example of BeCl2. If you were to draw the Lewis structure of BeCl2, you would end up like this, right? And Bl, it can be electron deficient, so it's fine for it to be like this. Now, as you can see, what we are gonna care about is what is only the central atom. Now, the central atom has what? Has two bonds, right? Two pairs of electrons that are bonded. So we take the central atom and we will consider it A, okay? Because we have a central atom, we will call it A. And then if we have two bonds that are single, of course, on the central atom, we will denote it by X. So here it's X2. But for example, if we had a lone pair on the atom, this would be considered as E, okay? So in this scenario, we don't have any lone pairs on the central atom. This is why we don't put an E. But in this scenario, we have a central atom A with two bonded pairs of electrons. So that's why it is X2. Now, what about the structure? Because it is AX2, look what's going to happen. We're going to have our central atom in the middle. And the two chlorine, like the two surrounding chlorine, they don't want to repel each other, so they're gonna keep the maximum angle they can, which is 180 degrees, okay? So from both sides, not actually both sides, on all sides, if you take it in a 3D structure and you turn it, and no matter which side you turn it, you will see that they are the farthest from each other as much as possible. Now, how do we know the geometry of a shape? This will require a little bit of memorization, okay? So the title of this page is How to Know Geometry of a Shape. First thing, you need to draw the Lewis structure. So draw Lewis structure. Okay, but let's say, for example, you have a resonance structure. So in case of a resonance structure, this is all, by the way, from chapter 3. Okay, so in case of a resonance structure, use the most stable or valid structure. Okay, this is step 1 on how to know the geometry of a shape. Step number 2 is to represent, look, represent central atom by, let me change the color now, I'll change this color, by A, okay? Then represent the lone pair by E, and then finally the bonded pair by X. Wait, no, I didn't use the red color. Let me undo this. So we will represent the bonded pair by X. Now what's the third and final step? It is to look at the table. So look at table. So the 3 steps in order to determine the geometry of a shape is, first of all, draw the Lewis structure. In case of a resonating structure, you need to use the most stable or valid structure. Step number 2, step number 2, you represent the central atom by A, the lone pair by E, and the bond pair by X. Of course, this is the bond on the central atom, and then the third step is to look where, is to look at the table. Now, here comes a very, maybe long, but very interesting part, which is now the table. On my physical copybook, it took me 3 pages. I don't know how much it will take here, but I'm gonna try and draw them my best because I prefer to draw it so it will be understandable and know how I'm drawing it. And then in the end, I will put a separate table that I found online, and then you can take a picture, you can use it, and you can memorize the structures. So the first thing I'm gonna do is I'm gonna separate this into a table. Okay, so this is what the table is going to look like. We're going to start with domains, lone pairs, species, and then I'm going to draw the geometry. I'm going to give the bond angle, and I'm going to give the name of the structure and an example of such a structure. So we first start with electron domains. What does it mean, electron domains? It means whether we have bonded pairs, lone pairs. These are electron domains. Now, in the first structure, we're going to have 2 domains, but we're not going to have any lone pairs. If that's the case, that means we have a central atom for sure, and we don't have any lone pairs, but we have 2 domains. That means it's going to be only bonded electrons, and we have 2, so it's going to be AX2, right? Let me just draw a line so it will fit. Oh, that's not nice. It's not neat. Now, let us draw the structure. For AX2, we start with the central atom A, right? It will have the bonded pair, right? And how much will be the angle? The angle here is going to be how much? It's going to be 180 degrees, okay? The name of this is what it is, a linear bond, okay? Some examples of this are BeCl2, BeH2, etc. Stuff like this. Now, after that, oops, what happened? Let me fix that. After that, we'll move on to what? We'll move on to 3 domains. So we start off in the 3 domains, right? And we always start off with how many lone pairs? We always start off with 0 lone pairs. If that's the case, then it's gonna be AX3. The species is gonna be AX3. And it will look something like this. We will have our central atom over here, and we will have 3 bonds like this, X, 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 and the angle between each bond is 120 degrees. So all of these are 120 degrees. Now, the name of this is a what? It is a trigonal planar, right? So it's in the shape of a triangle. It's a trigonal planar. Now, some examples of this are what? Are BF3, SO3, and etc. Okay, so this is 3 domains and 0 lone pairs. Now let's start. Let's say we will have 3 domains but 1 lone pair. if that's the case, then we would have what? We would have the species to be AX2E. But now you may be thinking, oh, but that's only 2 domains. No, we have 3 domains because domains include bonded pairs and lone pairs, okay? So in this scenario, look what it's gonna look like. We're gonna have, again, our central atom A, but this time it has 2 bonded pairs and 1 lone pair. What about the angles now? Each of the angles are now gonna be what? They're going to be different than the previous one. Now, the interesting part is that the angle between the lone pair and the bonded pair is greater than the angle in between the bonded pairs. Now, the angle in between the bonded pairs is going to be what? It's going to be slightly less than 120 degrees, right? Now, what's the name of this graph or the shape? This is called an angular or V-shaped or a bent structure. And some examples of these are SO2 and O3. So this is the 3 domains and 1 lone pair. Now we'll move on to the next one, which is 4 domains and 0 lone pair. So that will be AX4, right? So let me draw. I'm gonna need a bit of more space for this one. Okay, perfect. Now, look at AX4. We're going to start with our central atom A. Now, when we reach AX4, there's something very important we need to know. And that is when we start with the AX4, we're going to have out of the plane or like behind the plane, in front of the plane, or on the plane. Regarding AX4, this is how the structure looks like. We're going to have a bond here like this, a bond behind the plane, and a bond in front of the plane, right? Now, this is X, X, and this is also X, and this is also X as well. And the angle between any of the bonded pairs is gonna be 109.5 degrees. What is this structure called? The structure is called a tetrahedral, okay? Now, I know it's kind of difficult to imagine, but when I put the graph that I have, maybe it's gonna be much easier. So an example of this is gonna be what? It's gonna be CH4, Si, F4, etc., so on and so forth. Now, for this one, I'm gonna use up the whole space. This is what? This is 4 electron domains. We're gonna have 1 lone pair, and it's gonna be AX3E. In this scenario, look what we're gonna have. We're gonna have our central atom A, right? Now, the only difference is that we're gonna have X in the plane, we're gonna have X in front of the plane, and we're gonna have X behind the plane. Now, the only difference in this scenario is that we're gonna have a lone pair. Now, what happens? This lone pair is gonna push the bonds farther. So the angle between the lone pair and the bonds is greater than the angle between the bonds themselves. So now, the angle between the bonds is gonna be how much? It's gonna be slightly less than 109.5 degrees. Examples of these are NH3, PH3, and so on and so forth. Also another example, PBr3, PBr3. So these are just like all general examples of the domains. Now, for this one over here, we'll move on to the next domain. Let me change the color. The next domain, which is 4, but in this scenario, we will have 2 lone pairs. So now it's gonna be AX2E2. Okay, what about this one? Let me just take some space. There we go, perfect. Now, AX2E2, look what's gonna happen. We are gonna have what? We're gonna have our central atom. And as you can see, we're gonna have 2 atoms that are bonded. Now, if you only have 2 atoms that are bonded, it's way preferable to keep what? To keep them both in the plane. So now you're gonna have 2 that are in the plane. So what does this leave us? This leaves us with the 2 others, which are behind the plane and in front of the plane, to be what? To be lone pairs, okay? So this is a lone pair behind the plane, and this is a lone pair in front of the plane. Now, as we said, of course, the lone pair is going to push the bonds more. So the angle over here is going to be what? It's going to be slightly less than 109.5 degrees. Let me make the point a bit clearer. 109.5 degrees. Now what is this called? This is called angular, V-shaped, bent, right? And some examples of these are what? Are water, H2O, and SCl2. So this is the 4 domains and 2 lone pairs. After this, we will move on to what? We'll move on to 5 domains and 0 lone pairs. So that's gonna be AX5, okay? I'm gonna need some space for this. So I'm gonna take up a big amount of space. I'll bring this down a bit. Yeah, that's good. There we go. So now let us draw the structure of AX5. We start off with what? We start off with our central atom, A. Now, in this scenario, it's a bit complicated, but remember, we will have 3 bond pairs in the plane. So X, 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 3 of them are in the plane. And we're gonna have 1 behind the plane and 1 in front of the plane. So let's say that we chose this one to be behind the plane, and we chose this one to be what? To be in front of the plane. Perfect. Now, those in the plane, pay attention, those in the plane, the angle in between them is what? Is 90 degrees. So 90 degrees here and 90 degrees here. However, the one behind the plane and the one in front of the plane, the angle in between them is what? The angle in between them is 120 degrees. Now, something that's more important is that from this side of the plane, this being in the plane and this being in the plane, the total angle in between them is how much? Is 180 degrees. This is very important to keep in mind. So in this one, we have 3 different angles, which are 90 degrees, 180 degrees, and 120 degrees. And what do we call this shape? We call this a trigonal bipyramidal. Okay? Now, some example of this would be what would be PCl5. So basically, so far we've done 1, 2, 3, 4, 5, 6, 7. Now what you need to do very simply is you need to draw the Lewis structure, and you will see, okay, I'm gonna label the A to be the central atom, X if I have bonded pairs, and if I have a lone pair, and then I will see the species, and then I will look at the graph, and I'll remember the graph is like this, so I will choose this to be the structure, and I will draw it like this. Now, we will move on to the next species. I did the wrong color, my bad. I like to be color coded. Sorry if it's taking a bit of time, but I like to stay and remain color coded. It's very important for me. So anyways, let us now say that we have 5 domains. Yeah, 5 domains, but 1 lone pair. So it's gonna be AX4E. This structure is very, very, very important. It's a new structure. So please pay attention, it's very important. We'll first start with the central atom A, okay? Now, what did we say? We said we're gonna keep 2 in the plane, right? And 1 behind the plane, 1 in front of the plane. And that leaves us with the third one to be what? The third one to be a lone pair. Now, what happens? This angle here turns into less than 90 degrees. So in the plane and behind the plane, is gonna be less than 90 degrees, and then behind the plane and in front of the plane is gonna be what? It's gonna be less than 120 degrees, because again, the electron pair is pushing them or repelling them the most, and we call this structure a seesaw structure. Some example of this structure, I don't think they gave us an example of a structure, but just in general, this is called what? It's called a seesaw structure. Now we move on to the next one, which is what? If we have 5 domains and 2 lone pairs, so now it's gonna be a X3E2. So again, we will start with our central atom over here, right? And then we're gonna have what? We're gonna have 3 bonded and 2 lone pairs. In the scenario that we have 2 lone pairs, it's preferable to put the lone pairs on behind the plane and in front of the plane, okay? That means we're gonna have 3 that are what? That are in the plane. We're gonna have 1 behind the plane, and this is a lone pair, and 1 in front of the plane, and it is a lone pair. Now, of course, this lone pair is gonna be pushing more on these, so that means the angle here and the angle here is gonna be what? It's gonna be less than 90 degrees. And we call this structure a T-shape structure. Some examples of the T-shaped structure are ClF3 and ICl3. Now we move on to the next one. What is the next one? The next one is having 5 electron domains and 3 lone pairs. So now it's gonna be AX2E3. So now look what's gonna happen. It's gonna be the central atom, right? And we said that it's preferable if we have 2 or more lone pairs to put them in front of the plane and behind the plane. And we said that will leave us with 3, right? But we only have 2 that are bonded, so we'll put 1 here, and this will be the lone pair. Now, the angle here is 180 degrees. Why? Because they need to repel each other as much as possible from all sides. And what does it mean? This means that this is a linear structure. Some examples of a linear structure at AX2A3 is I3 minus and XeF2. Now, just like that, we finished from 5. We will move on to 6. What does it say in 6? 6, they only gave us 3 examples, but in the graph I'm gonna show you, I don't know what's happening with this. In the chart I'm gonna show you, they put more structures, but for now, we will follow the book, okay? So they said, let's say we have 6 electron domains, but 0 lone pairs. That means it's gonna be AX6. We will start with the central atom A, and we will have, of course, these 2 being linear to be as far apart as possible. And then we will have what? We will have 2 behind the plane, 2 in front of the plane, right? So X, 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 X. And now we will see that the angle between any 2 bonds is gonna be what? It's gonna be 90 degrees. Now, any 2 adjacent bonds, it's gonna be 90 degrees. So, what is this structure called? It's called an octahedral, right? And some examples of octahedral are SF6 and SECl6. Perfect. So that's 6 and 0, AX6. Now we move on to 6 and 1. Oops, I still had the thing on. So we'll move on to 6 and 1. So that's going to be AX5E. So what did they do in AX5E? They took our central atom and they did all of the bonds same as before, right? Now, how this is going to happen is that we're going to put the lone pair here in the plane, and everything else is going to be what? It's going to be an X. Now, what do we call the structure? This structure is a square pyramidal, and the angle in between 2 adjacent is going to be what? It's going to be less than 90 degrees. Some examples of a square pyramidal are IF5. Now, we move on to the last thing the book wants us to discuss, which is 6 electron domains and 2 lone pairs. So the species is going to be AX4 E2, okay? So here again, you're just gonna draw the basic AX6 structure, right? Now, what are you gonna do in this scenario? In the plane, you're gonna put the lone pairs, and everything else is gonna be what? It's gonna be an X. So what do we call this? We will call this a square planar. And some examples of a square planar are IF4 minus, XeCl4, and the angle between the forward and the backward is what? It is 90 degrees. So that's pretty much it for the lone pairs and their shapes. So I'm gonna put the chart now. So here we go. This is the chart. If you guys want to take a picture of it, if you want to study it, you can pause the video, you can do whatever you want. But here is the chart, okay, if you want to take the shapes into more accuracy. Now, after this, I'm just gonna move on to the hybridization. So we only have a couple of them that are hybridized. We have the first one, which is AX2, which is sp hybridized. Okay. Then we have AX3 or AX2E, which is what? Which is sp2 hybridized. And then we have AX4, AX3E, or AX2 E2, which is what? Which is sp3 hybridized. Okay, this is something important to remember. Now, after this, they're gonna ask us about the localized electron model. The localized electron model, which is referred to as LE, allows us to describe the covalent bonds in simple and complicated molecules, and all of this is based on the loose structure, the VSEPR model, and the atomic orbital types. Okay, so the localized electron models allows us to describe the covalent bonds in simple and complicated molecules, of course, based on loose structure, VSEPR model, and atomic orbital types. I repeated 2 times so that you would not forget it. Okay, it describes a molecule as a substance made up of atoms held together by shared electron pairs, either lone or bonded. So if they asked you, how does the localized electron model describe a molecule? You will say, it describes a molecule as a substance made up of atoms held together by shared electron pairs. And these electron pairs are either, of course, lone and bonded. Okay? And just like that, we finished 4.1. So now we'll move on to the next section, which is section 4.2. 4.2 talks about the polarity of molecules. So polarity of molecules. First of all, before we start, what is the definition of polarity? Or let's be more like clear and simpler, the definition of polar. If a compound is polar, or if an atom is polar, it reflects that it's strong, like stronger than the other atoms to attract an electron. So if we wanted to define polarity, actually, it would be better, not polar. It would be how strong an atom attracts an electron. This is the definition of polarity. Now, of course, there are 2 factors that determine if a molecule is polar or non-polar. So let me write factors determining polarity. The very first thing is what? The very first thing is the polarity of the covalent bonds. So the very first thing that determines the polarity of a molecule is what? Is the polarity of the covalent bonds. Now, the second thing after this would be what? The shape of the molecule. So, if you find out these 2 things, then you will know whether you're dealing with a polar bond or a polar molecule, or a non-polar bond or a non-polar molecule. Now, how do we calculate bond polarity? Very simply, bond polarity is what? Bond polarity is the difference between the electronegativity values of 2 bonded atoms. So bond polarity is delta En, the difference between the electronegativity values of 2 bonded atoms. Okay? It can be used to predict the polarity of the chemical bond. Now, also, from the bond polarity, we can determine if it's ionic, if it's a polar covalent, or a non-polar covalent, okay? We can determine this very simply by the delta En. Now, if the delta En is large, that means delta En is greater than or equal to 2.0, then we know that it is what? It is ionic. However, if delta En is smaller than 2.0, but greater than or equal to 0.4, then we will know that this is what? This is a polar covalent. Now, if delta En, which is the bond polarity or the difference in electronegativities, is smaller than 0.4 but greater than or equal to 0, then this is a non-polar covalent bond. Now, let's take an example of a non-polar covalent bond and an ionic, okay? The non-polar covalent would be Cl single bond Cl, right? Cl has an electronegativity of 3.0, okay, and 3.0. And also don't forget to use this Falkland bridge. This will help you know which is the most electronegative and which is the least electronegative. Now, of course, Cl and Cl, if you do the delta electronegativity, it's gonna be 0. And we said if it's equal to 0 or greater than it and less than 0.4, then this is what? Then this is a non-polar covalent molecule. Now, let's say we took another example, an ACl, okay? This would be what? This would be 0.9, and this would be what? This would be 3.0. So the delta En, now 3 minus 0.9 is 2.1. So this is greater than or equal to 2. That means it is what? That means it is for sure ionic. Perfect. Now, this would be like really easy if we're talking about just two atoms bonded together by one single bond. Now, let's say if you're dealing with bigger molecules, for example, CH4, I don't know, NH3, how do you know if this is polar or non-polar? Very simply, you're gonna check their geometrical structures. Okay, so I'm gonna first of all write conditions of molecular polarity. So the very first thing you're gonna check is what is the shape or the structure of the molecule, and you need to check if it's symmetrical or not. I'm gonna write down all of the shapes that are symmetrical. Of course, you can take them from above, how they are drawn, blah blah blah. You have AX2, AX3, AX4, AX5, AX6, okay, and AX4E2 and AX2E3. These 7 shapes are what? Are symmetrical. That means they're all what? They're all non-polar. All other shapes are polar, so all else polar. Now, the second condition is the most important condition in my opinion, and that is the surrounding electron domains, which is what? Which is mainly X for sure, need to be same element. Why? Because if we have different elements, we know that each element has their own electronegativity. So if we have different elements, they're each going to have a different pull on the electron. And this different pull might cause some to be more polar than others. And if you did the total polarization around the central atom, you would get that it's still polar. And this is not what we need. If they're all the same element and they're all symmetrical, then what's that going to mean? Then that means it's going to be a non-polar molecule. So anyways, that's it for chapter 4.2. We'll move on to 4.3. Now, I'm going to have to say that 4.3 is a bit long, so do bear with me. Now, all of the bonding we've been talking about is intramolecular bonding. So, bonding that we have been talking about is intramolecular bonding. And what does this mean? This means it's within a molecule. So, bonding formed within a molecule is intramolecular bonding. Now, we will leave intramolecular and we will go to a new type of bonding, which is what? Which is intermolecular. We may have heard this last year, okay? From the van der Waals forces, if you remember, okay? So intermolecular forces, okay? They are forces that exist between atoms or molecules to determine the state of matter, cause atoms to move in a certain way as well. So intermolecular forces exist between atoms or molecules. Notice it's not in molecules, it's between atoms or molecules to help determine a state of matter and allow atoms to move in a certain way. Now, of course, they are weaker than ionic, covalent, and metallic bonds, but they're also known as van der Waals forces. So, they are weaker than ionic, covalent, and metallic bonds, and they are also known as van der Waals forces. Now, something very important we need to know is that the energy or the enthalpy change that is used to change a state, for example, vaporization, condensation, all of this is used to break and build the intermolecular forces, which changes the state. Whereas the energy or enthalpy change to decompose, meaning to break down the molecule into its elements, this is used to break the intramolecular bonds. So I'm just gonna write a quick summary that enthalpy change of, first of all, state. This is intermolecular forces. But if it's the energy change of decomposition, then this is intramolecular. Now we move on to what we will move on to going deeper into the van der Waals forces. There are two types of van der Waals forces. What are they? The very first thing is the London dispersion force, the LDF. It's London dispersion forces. Now, what is the subtype, or like what is the type of bond that is in the London dispersion forces? It is the instantaneous dipole induced dipole. Okay, so this is instantaneous dipole induced dipole. All right. Now, before we get into a deeper conversation about the other type of van der Waals, let's focus on the London dispersion force. It is the weakest force ever found in a molecule. And of course, the only bond being the instantaneous dipole induced dipole, it's gonna be very weak. How does it happen? Very simply, we will have what? We will have two atoms, right? Let's say this is the positive nucleus of the atom, and it has 4 surrounding electrons. And this is also the positive nucleus, yeah, and it has 4 surrounding electrons. Now, the closer these atoms come together, look what's gonna happen. Of course, I forgot to draw the rest of the atom, okay? So when these atoms come closer together, look what's gonna happen. We will have a stretch in both of them. They will both become stretched. Now, you may ask why. Very simply, look why. Our positive nucleus is gonna stay aside, but our 4 electrons are gonna move to this side. Why? Because again, our positive nucleus is gonna stay here, and our 4 electrons are gonna move there. This is called what? This is called an attraction, because the negative and positive are attracting each other, but this is only for an instant, and then they will go back to normal again. Okay? So this is the first step, then the second step, and then the third step, they will go back to normal again. This is only if they come close to each other for a single second, and they will form what? They will form a bond. This bond here is called the instantaneous dipole induced dipole. It's called instantaneous because it lasts only an instant, and induced because they come close together and they will force this dipole to happen. It doesn't already exist, it's forced to happen. So this is why it's called an induced dipole. Now, what happens is that this will acquire a temporary, this will have a temporary negative charge, and this will have a temporary positive charge. So this is why they will attract each other. Okay? So in words, this is just like a drawing of how it occurs. I'm going to write on the new page in words what is an instantaneous dipole. An instantaneous dipole, induced dipole, is a temporary dipole that occurs when an atom or a non-polar molecule acquires a temporary partial negative, this means partial negative charge on one end and partial positive on the other. Okay, so this is all we need to know for the London dispersion forces IDID. It's the weakest force, and we just explained how it happens. Now, the second type of van der Waals force is what it is, the dipole-dipole. Now, of course, the type of bond is the permanent dipole, PD. We say PD twice because I don't know why actually, but it's permanent dipole. Now, why do we call it a permanent dipole? Because there's always a dipole and a constant force of attraction between the positive and negative ends in this molecule, okay? So if we want to talk, we will say there is always a dipole and constant attraction between positive and negative ends of the molecule. Of course, we know that this is the stronger van der Waals force. It's stronger than the IDID. So now let us compare their strengths. Of course, what we need to know for both IDID and PDPD is that the greater the number of electrons, the greater the force. Now, what exactly does this mean for the instantaneous dipole induced dipole? Very simply, I'm just gonna make like a small separation over here. For the IDID, of course, we're gonna be determined on the number of electrons as well as with the shape. Same thing with the PDPD, but it's more towards the number of electrons. So the greater the number of electrons in the PDPD, the greater the force. Now let's take a deeper talk in the electrons. The more electrons we have, so the greater number of electrons, the larger the electron cloud. The larger the electron cloud, this means the easier it is to distort. The easier it is to distort or polarize. It means polarization, and distort is the same thing. So distort or polarize the cloud, which means that the induced dipole, instantaneous dipole, induced dipole is gonna be stronger, right? I don't think it's gonna fit. I'll just try to make it fit. So it's gonna be stronger. And what does this mean if it's stronger? So more energy needed. That means boiling point is higher. So very simply, what am I trying to say over here? If you go back to the induced dipole, the instantaneous induced dipole, you will see over here that their shapes distort, right? Their shapes distort in order for them to form this instantaneous dipole. Now, they're saying if there's a greater number of electrons, that means the electron cloud is going to be greater and larger. If it's larger, it's going to be easier to distort and change the shape. That means it's going to be easier for the instantaneous dipole to occur. That means it's going to be stronger. And when it's stronger, what does this mean? It means we need more energy to separate. So definitely if we need more energy to separate, that means our boiling point is going to be higher. Now, this is in regards to the instantaneous dipole-induced dipole for the number of electrons. If we're talking about the shape, the more linear, the greater the ID forces. The more linear, the greater the ID forces. What does this mean? This means in the exam, if they give you two molecules that have the same number of electrons, okay? If they have the same number of electrons, right, but they have different shapes, one is more linear than the other, then you will choose the one that is more linear, because the more linear, that means the greater the ID forces, okay? Okay, so that's pretty much it for the van der Waals forces. Now we move to a brand new force, which is what? Which is hydrogen bonding. Now, it's not a van der Waals force, but it is an intermolecular force, so it's hydrogen bonding. What is this type of force? It's a specific dipole permanent force. It's very specific. It occurs to only 3 atoms, okay? Where a hydrogen, which will have a partial positive, will form a bond with either fluorine, oxygen, or nitrogen, because they're highly electronegative. We don't take chlorine, only fluorine, oxygen, nitrogen. So, okay, if they asked us what is hydrogen bonding, it is a specific dipole permanent force that exists between a hydrogen bond and between a hydrogen and fluorine, oxygen, and nitrogen, as they are highly electronegative. Now, let's take it like this, okay? Let us say we have an atom over here, right? Let's say this is an atom, I don't know, whatever is here, and then we have a hydrogen over here. And then we have another atom, and we have either fluorine or oxygen or nitrogen. I prefer to say it's fluorine, let's say, for example. What happens is that the hydrogen will form a partial positive, the fluorine will form a partial negative, right? And the fluorine will have a lone pair, okay? So due to this lone pair, the deficit hydrogen is gonna want to get attracted to the lone pair. So this is how the bond forms. I kind of drew it wrong, to be honest, because do you remember from chapter 3, it's supposed to start from the lone pair to the deficit. So very simply, hydrogen of one atom forms a partial positive and FON form a partial negative, and the lone pair attracts the hydrogen, and thus we will have what? Thus we will have thus forming a hydrogen bond. So now let us rank the strength of the bonds, okay? We first start with the instantaneous dipole-induced dipole. It's the weakest. Then comes the permanent dipole, permanent dipole. Then comes the hydrogen bond. Now these are the comparison of strength in the intermolecular forces. Now, of course, what you need to know, again, as the number of electrons increases, the boiling point will increase because of literally whatever we discussed. So now we need to talk about the graphs for the hydrogen bonds. We know that hydrogen bonds occurs only between oxygen, fluorine, and nitrogen. And because they are the strongest bonds, they will require the most energy. So if we were to draw for, let's say, H2O, H2SE, and H2TE, right? Oh, and I forgot H2S as well. If we were to draw, it would be the highest point, then it goes down really low, and then it starts increasing slowly but surely. This is what the graph is supposed to look like. Now, this is an example with oxygen. Now let's take another example. Another example. So we have hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide. It will look something like this. We start from the top and then we go to the minimum, and then it starts increasing slowly and then slowly. So it will look something like this. Now there's a last type of dipole, which is an ion dipole, and this is the strongest dipole. It's stronger than the dipole. So that means it's stronger than hydrogen bonds, okay? So the ion dipole occurs between ions, so between ions and molecules. And these molecules need to be what? They need to be polar. So it occurs between ions and polar molecules. They are stronger than dipole-dipole forces. Now, why do we need to know about the ion dipole? It's important in the solubility of ionic compounds in polar substances. So, it is important in the solubility of compounds in polar solvents. Now, of course, how do we determine the solubility? We have a set of rules, so solubility rules. First thing we need to do, of course, it needs to be between what? Between a comparison between the solute and the solvent. What does this mean? You take the solvent and you list all of the forces you can find. Then you take the solute and you list all of the forces you can find. And then you compare the strongest force with the strongest force. If the interactions are similar, then it's soluble. If they're different, then it's insoluble, okay? So, if interactions are similar, then it is what? It is soluble. Otherwise, if it's different, then it's what? It's insoluble. And of course, the stronger the interaction, so stronger the interaction, the higher the solubility. Now, here, this is not really that necessary, but I'm still gonna write it. In large biomolecules, non-covalent interactions, which are intermolecular forces, occur between different regions of the same large biomolecule. Example, DNA and proteins. So, in large biomolecules, non-covalent interactions, which are basically intermolecular forces, occur between different regions of the same large biomolecule. And some examples of these are, of course, DNA and proteins. Examples being DNA and proteins. Now, of course, the structure and function of many biological systems depend on the strength and nature of the various intermolecular forces. So DNA, proteins, these all depend on the various, on the strength and the nature of the various intermolecular forces. Now, what are some physical properties that depend on the, let me write some physical properties that depend on strength and nature of the various intermolecular forces. They are actually a lot. They are surface tension. They are capillary action. They are viscosity. They are the volumes of mixing. they are hardness, they are vapor pressure, they are the boiling point, the melting point, and then the solubility. Now, after this, what do we have? Oh yes, now it is a guide on how to compare two substances to see which is stronger. So comparing two substances, you need to always follow these 3 steps. First thing is to identify intermolecular forces in the substance. You need to identify every single intermolecular force, whether it's the LDF, the dipole-dipole, the hydrogen bonding, or the ion dipole. You need to list them all and you need to state, okay, these are the intermolecular forces. Now, second thing, you will take the strongest with the strongest. You will say, okay, I have a hydrogen bond here and a hydrogen bond here. Now, which hydrogen bond is stronger? In order for that to happen, you will need to compare their strengths. Okay? Now, after that, you'll be able to do what? You'll be able to explain the variation in the physical property. That's it for 4.3. Now we'll move on to the last section, which is 4.4. And this talks about the anomalous properties of water. Now, what exactly does this mean? We have 4 anomalous properties of water. The first one is a high boiling point and melting point. Second thing is that solid ice is less dense than water, which doesn't make sense because usually solids are more dense than their liquid form. So it's less dense than water. Third one is a high surface tension. And then the last one is what is a universal solvent. Now we will discuss each and every one of these in depth. I will write just a brief summary about each one. The first one is the high boiling point and melting point. Now, why is there a high boiling point and melting point of water? This is due to the extensive hydrogen bonding between water molecules. What does this mean? We have a water molecule, right? It's an oxygen with 2 hydrogens. Now we have another water molecule, which is what? Another oxygen with 2 hydrogens. And then we have a third water molecule, which is another oxygen with 2 hydrogens. Now the thing about these 3 is that they form hydrogen bonds. If you drew the Lewis structure of water, it would be like this. It's oxygen, hydrogen, hydrogen, and then the 2 lone pairs on oxygen. Now let's draw another one nearby. Let's draw another one like this. Oxygen. Let me bring it a bit down actually. So we will have an oxygen here, hydrogen, hydrogen, and then the 2 lone pairs. So this is what is in water, to be honest. This is what we can find in water. Now, the extensive hydrogen bonding, a single water molecule will form 2 hydrogen bonds. Why? Because the oxygen, which is the one with the slight negative, has 2 lone pairs, meaning it will form a hydrogen bond with this partial positive. And then if we drew another one over here, right? This will have a slight partial positive, and this will form another hydrogen bond. So it forms 2 hydrogen bonds due to the presence of 2 lone pairs on each oxygen atom, and 2 partially positive hydrogen. Okay, so this is why it has a very high melting point and boiling point. This is due to the extensive hydrogen bonding, because each oxygen will form 2 hydrogen bonds, so it will be very, very strong. This is the first thing we discussed. Now, the second thing we are discussing is the density. Why is solid ice less dense than liquid water? Well, very simply, solid ice water molecules, it's a long start, are arranged in a rigid 3D lattice in rings of 6, in which each oxygen is surrounded by a tetrahedron of the hydrogen atoms, in which each oxygen is surrounded, I forgot how to spell for a second, is surrounded by a tetrahedron of hydrogen atoms. The large bond length of the hydrogen bond forms an open lattice which is filled with empty space. So the long bond length forms an open space, or not an open space, an open lattice with empty space. So I think I need another page to actually draw what's happening. So we will have water, right? This is the water over here. And then we will have the structure of the ice, which is like this. I think I keep on drawing 5. Wait, let me fix it a bit. Okay, so this is what it looks like. And of course, there's in the back as well. So if we did link them all together, it would look like this big structure. And this is basically what is found in the ice, right? Now, because of the long bond length, there will be a lot of spaces. And these spaces will be filled by, like, empty space. And this will, like, technically make them less dense because there's a lot of empty space, right? So instead of them sinking to the bottom, they will end up floating on top. Now, anyways, aside from this, we will move on to the third thing, which was a high surface tension. Surface tension. What does it say in the high surface tension? Due to the significant hydrogen bonding. So let's say this is the water molecule, the waters, right? And there's a water molecule here, water molecule here. Basically, the whole thing is filled with water molecules. Just give me a second. Okay, so this is what it looks like. Of course, there's gonna be hydrogen bonding, right? Hydrogen bonding, hydrogen bonding, hydrogen bonding. I'm just trying to do as much as possible. But basically, there's gonna be a lot of hydrogen bonding, right? Now, due to the so many possibilities of hydrogen bonding and these so many like hydrogen bonding in the end, they will become so strong and so close together. And due to this, they will have a very high surface tension. And then insects like mosquitoes will be able to walk on the water, okay? So for the surface tension, we say due to significant hydrogen bonding, water will form a lattice at the surface, and this will cause water to have a high surface tension. So what do we say? H bonding forms a lattice. Now, last but not least, it is the universal solvent. Now, of course, water is the universal solvent. You can literally dissolve a lot of things in water. That's like tea, sugar, salt, millions of things. You can dissolve it in water. Now, why is water the universal solvent? Because ionic and molecular compounds can dissolve in it. Because ionic and molecular compounds dissolve in it. Now, there's gonna be what? In water, if we're talking ionic-wise, there's gonna be what? There's gonna be an ion-dipole interaction. For example, let's say we have an ACl, we separated Na plus and Cl minus, and then we have a water molecule. Look what happens. Because Na is positive, the partial negative oxygen is gonna turn to it, right? So then, what does this mean? This means that everywhere around it, the partial negative oxygen is gonna be facing it, you know? Now, for Cl minus, it's opposite. Cl minus is negative. What does this mean? This means, very simply, that the partial positive hydrogen are gonna be facing towards it, right? So it's the opposite of the Na+. The Na+, it's the partial negative oxygen that's facing it, whereas in the Cl-, it's the partial positive hydrogen that is facing it. And due to these, we have what? We will have an ion dipole interaction. And as we said, these are stronger than hydrogen bonds, so this is why they will dissolve in water. Now, this is for ionic compounds. What about molecular compounds? Molecular compounds that dissolve in water are usually polar molecules. So this is basically what we need to know. My bad. Molecular compounds that dissolve in water are generally polar. For example, let us take ethanol. Ethanol dissolves in water. So it's CH3CH2OH. Okay, we will put it in water. So look what happens. We will have a separation, right? We'll have CH3CH2 over here. Then we have O with the double bonds. Don't forget about them. And then it has a partial negative. And then we will have hydrogen, which will have a partial positive. And then we'll have a water molecule over here, which will have H, a partial positive, oxygen with the double bond, and then hydrogen with the partial positive. And then over here, we will have the same exact scenario. Let me just rotate this. Over here, we will have the same exact scenario. So look what will happen now. What happens now is that this will form a hydrogen bond, and this will form a hydrogen bond, and due to this, it will dissolve. Now, very simply, this is it for this chapter. Thank you so much, guys, for watching. I hope you enjoyed, and have a wonderful day.